Have you ever thought about how you'd find the area of a really, really weird curvy shape? Well, in calculus, there's a name for that. It's called integration, and it's all about finding the area under a curve. And believe me, while it sounds pretty simple, it can be a surprisingly tricky and fascinating puzzle to solve. Now, you might remember from math class that, yeah, sometimes you can find this area perfectly. You just plug into a formula and you're done. But what happens when there is no simple formula? What do we do when finding that exact, perfect answer is just incredibly difficult, or maybe even impossible? Okay, this right here is what we're talking about. The definite integral is just the technical term for this exact shaded area you see. It's the space under the curve of some function locked between 2 points, a and b. It's a really simple idea to look at, right? But actually calculating it, well, that's a whole other story. And that's really the heart of the problem. For some super common, super important functions, like the one that gives us the famous bell curve in statistics, there is literally no way to write down the exact answer using regular math functions. And it's not like we just haven't found it yet. No, it's actually been proven to be impossible. This brings us to the big question then. If a perfect, exact answer is completely off the table, what's our game plan? We can't just throw our hands up and give up. The only way forward is to get a really, really good approximation. All right, so let's start with the most obvious approach. If you're trying to approximate a curvy area, why not use a simple shape that we already know how to calculate perfectly? And what's simpler than a rectangle, right? This leads us to our very first method, the midpoint rule. The whole idea is just to draw one rectangle. The trick is how we set its height. We make the top of the rectangle hit the curve right at the dead center, the midpoint of our interval. And as you can see, it's not a perfect fit. Some of it sticks out, some of it is left behind, but hey, it's a simple place to start. So the area is just the width of our interval times the curve's height at that one midpoint. It's super fast, super easy. But, those gaps and overlaps are kind of telling us we can probably do better. So can we? Oh, for sure. Instead of a totally flat-topped rectangle, what if we used a shape with a slanted top? Let's check out the trapezium rule and see how it builds on that first idea. See the difference here? Instead of using the midpoint, this method just connects the start point and the end point of the curve with a straight line. That gives us a trapezoid, and you can already see it seems to follow the curve a little more closely than that flat rectangle did. The logic here is pretty simple. We calculate the area of that trapezoid. It's just the width of the interval multiplied by the average height of the two endpoints. It's a neat little upgrade, but that straight line, it's still not a curve. And this is where things get really clever. I mean, think about it. If we're trying to approximate a curve, why are we using shapes with straight edges? Let's bring in a method that uses a curve to approximate a curve. This is Simpson's rule. Whoa, now look at how much better that fits. Simpson's rule uses the start point, the end point, and the midpoint. Then it fits a parabola, a simple U-shaped curve, perfectly through all three of those points. This parabola can actually bend and flex to hug the original function, giving us what looks like a much, much closer approximation. So the big idea here is that we're swapping out our original, maybe impossible to integrate function with a simple parabola that we can integrate exactly. It takes a tiny bit more math, but just looking at it, you'd guess it's totally worth it. But is it really that much better? Okay, so now we have our three contenders, the simple rectangle, the slanted trapezoid, and the curvy parabola. To figure out which one is actually the champion, we need to look not just at how they work, but at how badly they mess up. It's time to analyze their error. Right, let's put them head to head. It's not enough to just say one looks better. Math lets us be super precise about how the error in our guess behaves. The answer is all about how fast that error shrinks as we make our slices smaller and smaller. And here it is. This is the aha moment. The error for both the midpoint and trapezium rules gets smaller based on the width of our interval cubed, which, is pretty good. But just look at Simpson's rule. Its error shrinks based on the width to the 5th power. That is a massive, massive difference. Let's put that into perspective. Say you cut your interval width in half to get a better answer. For the first two methods, your error gets 8 times smaller. That's great. But with Simpson's rule, doing the exact same thing, your error gets 32 times smaller. You get way more accuracy for basically the same amount of effort. So,
The takeaway here is crystal clear. By using a slightly more sophisticated shape, a parabola instead of a straight line, Simpson's rule gives you this huge, outsized return in accuracy. It is, for that reason, just a tremendously powerful tool.
And of course, the secret to making any of these methods even more accurate is actually really simple. You just chop the problem into more, smaller pieces. Instead of one big rectangle or one big parabola, we can use hundreds or thousands of tiny ones and just add up all their areas. We call this a composite rule, and it lets us get as close to the true answer as we could ever need.
And that kind of leaves us with one last big thought. We've seen how to get better and better approximations, but in the real world of science and engineering, you can't just keep approximating forever. At some point, you have to stop and decide, yep, that's close enough. So the ultimate question isn't just about math. It's a practical one. How do we know when to stop?